Refer to the table of densities at the right to answer the following questions. So we have a list of densities here, different metals, aluminum, titanium, zinc, so on, and their densities given in grams per milliliter, or the number of grams for every 1 milliliter. We're also given a graph, an empty graph of mass versus volume. And they want us to sketch a graph of mass versus volume for titanium, copper, and mercury. Let's start with titanium. What do we know about titanium? Well, I can look at my table here, and I can see that titanium has a density of 4.54 grams for every 1 milliliter. Let's make a note so that we can remind ourselves the meaning of these numbers. I'm going to rewrite grams per milliliter as the mass of 1 milliliter. The mass in grams of 1 milliliter. Remember, by the way, that cubic centimeter, that's the same as milliliter. Milliliter is normally used to measure to measure the volume of liquids, and cubic centimeter is normally used to measure the volume of solids, but they are equivalent units. They mean the same thing. So if I look at 4.54 as the mass of 1 milliliter, then I can imagine that this is 1 milliliter. I don't need to imagine it, it is. Let's label our axis here. 1, 2, 3, 4. And I just need to find now 4.54 grams on my y-axis here. Well, if we're counting by tens, right, this is 10, 20, 30, 40, 50, then 4.54 would be about there, maybe. And so my first point on this graph is going to be right there. That would be the mass of 1 milliliter or 1 cubic centimeter of titanium. Well, if I doubled my mass, or if I doubled my volume of titanium from 1 cubic centimeter to 2 cubic centimeters, then I'm also going to double my mass of titanium. So I'm going to double from 4.54 to, 9.08, which means that when I'm here at 2, I'm going to be about here at 9.08. So I'm going to put my second point right here. I know this is kind of hard to draw so small. You'll see why we need a graph this big eventually. But I'm going to continue counting by 4.54s. I'm not going to be like super accurate about it because I know it's hard for you to like divide up these tiny little squares with much accuracy. So I'm just going to eyeball it. I think 4.54 up again would be like that. And then maybe right here. Now I'm not that confident in this line. So what I'm going to do is I'm going to skip all these dots right in here. And instead I'm going to jump to 10 cubic centimeters. So if I have 10 cubic centimeters, how far up should I go on this graph? How many grams would that be? Well, I know that 4.54 is the mass of 1 cubic centimeter, right? 4.54 grams equals 1 cubic centimeter. And now I just asked you, what if we had 10 of them? Well, now this is like the question from the last page, right? If we have 10 times as many cubic centimeters on the bottom as we do on the top, then we should also have 10 times as many grams, yeah? So I'm going to notice that we need to multiply by 10 here. And if I'm going to multiply by 10 here, then I need to multiply by 10 on my other side too. So 4.54 times 10. You can get your calculator out if you don't trust me, but this one is 45.4 grams. Is the mass of 10 cubic centimeters. 45.4 grams. So I'm going to find that on my graph. Looks like it's going to be about right there. No, it's not. It's going to be a little bit above that, right there. So we'll put my point about right there. And yeah, it looks like I did a pretty good job. And let's go ahead and connect these dots. When you're doing graphs like this, I don't need it to be perfect. I never need it to be perfect. I just need it to be recognizable that like you're roughly in the right spot. You know what I mean? Let's do our next line. Copper. So now we want do the exact same thing, but use a different density, right? And so therefore a different slope. Well, I know that copper has a density of 8.96 grams for every 1 milliliter. I'm going to write that like this. 8.96 grams equals 1 milliliter. Now this time I'm going to be a little bit smarter. I realize now that I really only need that 10 point. That mass, I need to figure out what the mass of 10 cubic centimeters is, and then I can skip all these in-betweeny dots. So I'm going to do that right away. 8.96 grams for 1 milliliter. What if I had 10? Well, we can see again, we have 10 times as many milliliters between the top and the bottom, so we should also have 10 times as many grams. So I'm going to do 8.96 times 10. Gives me this time 89.6 grams. So about 90. So I'm going to go 10 milliliters or 10 cubic centimeters. I'm going to find 90 on my graph. And here it is. So I'm going to come a little bit below that line. Just a tiny bit. We're going to go right there. Now maybe it would have been helpful to add in some other dots, because it's easier to connect the dots when we have more dots to look at. But if I had a ruler, this would be no problem at all. And look at that. I did pretty good, I think, connecting that dot. Okay, let's do the last one, mercury. Mercury looks like our densest yet, with a mass per cubic centimeter of 13.55. I'm going to do the same trick that I did with copper. If I know that 13.55 grams is the mass of 1 cubic centimeter, then I need to figure out what 10 cubic centimeters is. That way I can make my graphing job a lot easier. Again, we have 10 times as many cubic centimeters, which means that we should also have 10 times as many grams. 13.55 times 10 gives me 135.5. Oh no. Looks like I can't do 10 cubic centimeters because I can't go all the way up to 135 on my graph, right? I only go up to, well, that's 110, that's 120. I could guess, but I would rather pick a point that's actually on my graph. So I'm going to come down a bit. Instead of doing 1 cubic centimeter, instead of doing 10 cubic centimeters, let's try 8 cubic centimeters. I could figure out the actual number, but I wouldn't really expect you to do that. You just do this guess and check thing. So let's figure out how many grams are in 8 cubic centimeters. Well, this time I have not 10 times as many, but I have 8 times as many cubic centimeters on the bottom as I do on the top. So then I'm going to also multiply my grams by 8. 13.55 times 8 times as many. I can do that on my calculator here. 13.55 times 8 gives me 108.4 grams is the mass of 8 cubic centimeters. 108.4. That number I definitely do have on my graph. So let's find 8. It's right there. And we'll come up until 108. Oh goodness. Let's zoom out for this. So 8 cubic centimeters, and I need 108, which is about right there. And now I can play connect the dots again. If you're wondering how I know to start at 0 each time, well, it's because, I mean, just think about it. If we have 0 milliliters of our substance, and we're taking up 0 cubic centimeters of space, then, like taking up no space, then we can't have any mass, can we? So if we have 0 milliliters of copper or mercury or titanium or any metal, then we should also have 0 grams. That's how I decide to start at 0, 0. I know we need a point at 0, 0. On our density labs, some of us decided that we were going to put our some of us decided we were going to connect our dots or put our lines of fit, something like that, or even like this, right? And this doesn't make sense at all, right? Neither of these. Because if we have 0 milliliters, we should also have 0 grams. We can't have 0 milliliters and some number of grams. Or we also can't have some number of milliliters but 0 grams. It doesn't work that way. So make sure that all of your density graphs always go through the origin at 0, 0. This is wrong. Let's put an X through this. Okay. So there we go. That's what our graph should look like. We should have 3 very distinct lines with different slopes. Let's move on to 6. You made some cubes out of each metal in the table that each measures 2 centimeters on every side, all except mercury. Why can't you make a cube out of mercury? Well, you might not know this. Well, we should know this by now, actually, because I've talked about mercury a bit since we did this packet. Mercury is a liquid. That's the answer it's looking for there. Because mercury is a liquid, we can't make a solid out of it. Sorry, we can't make a cube out of it. Now, if we got mercury cold enough, if we froze it, then we totally could make a cube out of it in the same way that we can make a cube out of frozen water, ice. But at room temperature, mercury is a liquid. And mercury is the only metal at room temperature which is a liquid. Anyway, that's just sort of an aside. Now it's asking us what is the volume of each of these cubes in cubic centimeters. Well, I know that each of these cubes measures 2 centimeters on every side. Let's draw a cube. I'm going to draw a cube like this. It's not a perfect cube, but it doesn't need to be. And I know that this cube, in case you're having trouble seeing my cube, we know that this cube measures 2 centimeters on every side. So that's 2 centimeters by 2 centimeters by 2 centimeters. In all 3 dimensions, it's 2 centimeters. And that's the definition of a cube, right? We need to have equal side lengths all the way around. Well, I know from my geometry class that the volume, or the formula for volume of a cube, can be calculated length times width times height. Or I guess that's really any rectangular solid. For a cube, I guess we really just need to do side length cubed, which is, in this case, 2 times 2 times 2. Just to be clear, that is 2 centimeters times 2 centimeters times 2 centimeters. That's how we find the volume here. Well, I know that 2 times 2 times 2 is 8. I need to figure out my unit here. Well, I have centimeters there, and a centimeters there. They're all being multiplied together, so I'm going to write centimeters cubed. And that matches the unit that they're asking for, right? They want to know the volume of each cube in cubic centimeters. That's 8 cubic centimeters. That's the number I'm going to put here. By the way, in case we're having trouble visualizing what a cubic centimeter is, I can draw it out for you like this. Let's erase my marks here. If this is a cube that measures 2 by 2 by 2, if I were to break this up, sort of like this, we can see where those cubic centimeters actually come from. This here is 1 cubic centimeter. Now we can see it a little clearer, right? We got 1, 2, 3, 4 cubes here, cubic centimeters. Each of these blue cubes, of course, measures 1 by 1 by 1 centimeter. And then we got 1, 2, 3, 4, and 1, 2, 3, 4 behind it again. So that's the other 5, 6, 7, 8. That's another way that we could figure this out. We don't even have to do math. We can just draw our cube and then divide it into cubic centimeters and then count them up. So that's 8 cubic centimeters again. Okay, and it also wants to know our volume in milliliters. Well, we already said, I think in the last video, that 1 cubic centimeter is 1 milliliter. Actually, we did it up here, right? So these are the same unit. They're measured the same way. So I'm going to put an 8 there as well. 8 cubic centimeters is 8 milliliters. Okay, easy peasy. It wants us to find the mass of these metal cubes, and it says show your work below. Oh, okay, let's do the lead first. My lead cube. What do I know about lead? Well, from our density table up here, we definitely know the density of lead. Right? I can see that the density is 11.35 grams for every 1 milliliter. Let's write that down here. 11.35 grams for every 1 milliliter, which means 11.35 grams is 1 milliliter. Yes? Well, how many milliliters is our cube? It's not 1, right? It's 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to do what we did up at the top of this page. I'm going to put 8 here. And now I need to ask myself, what number of grams goes with 8 milliliters? Well, hopefully, we should be able to see that in order to get from 1 to 8, we need to multiply by 8. Yeah? Because that question that I asked myself just now in my head was, is 8 bigger or smaller than 1? Obviously, it's bigger. So how many times bigger is it? Well, it's 8 times bigger. And if we have 8 times as many milliliters on the bottom as we do on the top, then we should also have 8 times as many grams. I don't know why I switched colors there. We should also have 8 times as many grams. So to figure out the answer to this question mark, I'm going to say 11.35 grams times 8 times as many of those grams. And when I do my math, let's do it on my calculator here. 11.35 times 8 gives me 90.8 grams. Beautiful. So here I'm going to say 90.8 grams. Now to save a little bit of time, I'm only going to do nickel. I'll leave zinc for you to do. And let's do that now. I'm going to do it the same way. I'm going to come up to my density table. I'm going to figure out what the density of nickel is. I'm going to find it here. 8.90 grams for every 1 milliliter. And I write that here. 8.90 grams. That's what it was, right? I forgot. 8.90. That's right. 8.90 grams for every 1 milliliter. Again, here, for this cube, we have 8 milliliters, not 1. So I'm going to say, okay, 1 times what? Times 8 gives us 8. So then, again, 8.9 times what? Times 8. We have 8 times as many grams because we have 8 times as many milliliters. So to figure out the answer here, I'm going to say 8.90 times 8. Do that on my calculator. 8.90 times 8 gives me 71.2 grams. Easy peasy. And like I said, I'll leave zinc for you to do on your own. You should be able to figure it out now with these two done. Let's move on to number 7. Alicia's cheapskate boyfriend gave her a ring that he claims is 24 karat gold. That is pure gold. Alicia is skeptical because he's a cheapskate boyfriend, I guess. After chem class the next day, she measures the mass of the ring, finds the volume of the ring by water displacement, and then calculates the density of the ring. Should she treasure the ring as his first truly generous gift to her, or throw it at him the next time he walks by? He wants us to defend our answer. Okay, so I know that she found the mass of this ring, probably just by putting it on a balance, and she found that it was 15.28 grams. And we know that she also used water displacement to find the volume. Just to remind you, water displacement is when we have a graduated cylinder filled with water to a certain point. We can read what that initial volume is. That volume of water at the beginning, the initial volume. And then we can add an object in this case, a ring. So we'll throw a ring in here. And when we put the ring in this graduated cylinder, because that ring is taking up space in the graduated cylinder, it displaces the water. It pushes the water out of the way, because if the ring is occupying that space, the water can't be. And when it does that, it's going to push the water level up to a new point right there. And we can call that the final volume. And this is how water displacement works. We can take these two volumes, the initial and the final, the before we put the object in and the after we put the object in, and we can subtract these numbers. So I'm going to say final minus initial equals the difference. The difference in volumes, that is the volume of the object. All right, so I know we need to do final minus initial. And we got 43.7 mils minus 42.2 mils. When I do that subtraction, I'm going to get 1.5 milliliters of ring. That's how much, that's the volume of the ring that, does he have a name? No, Alicia's boyfriend gave her. 1.5 milliliters. Well, now we know the number of milliliters, or the amount of space that this ring takes up, and we also know the number of grams that it is heavy. So if we want to find the density of this ring, let's remind ourselves what density is. What is density? We should know by now that density is the number of grams for every 1 milliliter, or cubic centimeter, right? If we want to use cubic centimeter. If this is unclear to you, the number of grams for every 1 milliliter, if that's a little bit like, what does that mean? I don't really get it. Then here's another way of thinking of it. And this is from the top of our page that we already said. The mass of 1 cubic centimeter of the substance. The mass of 1 cubic centimeter of the substance. 15.28 grams and 1.5 milliliters. Let's try writing this like this. 15.28 grams is the same as, or equals, takes up 1.5 milliliters of space. 15.28 grams equals 1.5 milliliters. And I know that density, right, is the number of grams for every 1 milliliter, or 1 cubic centimeter. So I know that I need to find this number, the number of grams that goes with 1 milliliter, based on this information. All right, so this is the first time that we have something that's a little bit tricky. Let's come back up here and remind ourselves what we did. All right, this is that math setup that we're going to see a million times in this class. 11.35 grams of lead was 1 milliliter. And then we wanted to know the number of grams that went with 8 milliliters. And for this relationship between 1 and 8, it's really easy to see that 8 is 8 times bigger than 1. Right? Down here, it's not as simple. right? We have weird numbers. We have decimals now. But remember that first question that we need to ask ourselves is 1 bigger than or smaller than 1.5? Well, in this case, it's smaller than. But our question is, how many times smaller is it? Yeah, what do I need to divide by, or what do I need to multiply by to get from either 1.5 down to 1 or 1 up to 1.5? You can do this either way. For me, it's a little bit easier to see that in order to get from 1 up to 1.5, I need to multiply by 1.5. Okay, now that might be easy for you to see. It might be easier for you to see that 1.5, to get down to 1, we need to multiply by 2/3. Yeah, or 0.667. Your brain might like this way better. My brain happens to like this way better. But we should be able to see some sort of a relationship between the numbers 1 and 1.5 via multiplication or division, whatever you need to do. Let's follow my example here. To get up from 1 to 1.5, we multiply by 1.5. Now, if we multiply by 1.5 to get from the bottom up to the top, that is, we have 1.5 times as many milliliters on the top as we do on the bottom, then we should also have 1.5 times as many grams on the top as we do on the bottom. So I'm going to draw symmetrical arrow, right? The exact same, facing the same way, and I'm going to put my same conversion factor of 1.5. This is showing me that to get from whatever this number is up to 15.28, we need to multiply by 1.5. So I'm going to write question mark times 1.5 equals 15.28. I hope that we can see that in order to figure out what that question mark is, well, we just need to reverse the direction of this arrow and change our 1.5, change our times to a divide. Yeah, so it becomes 15.28 divided by 1.5 equals question mark. Well, now we can punch this into our calculator. I got 15.28 divided by 1.5 gives me 10.19. 10.19 what? What's our unit on here? Let's find our question mark again. Right here, grams. This 10.19 grams is what? The mass of 1 cubic centimeter. So I'm going to write that as 10.19 grams per cubic centimeter, or 10.19 grams for every 1 cubic centimeter. That is the density that we just solved for. 10.19 grams is the number of grams that goes with 1 milliliter or 1 cubic centimeter. All right, so that is our density here of this ring. Well, how should we know whether or not she should treasure the ring or throw it at him? What do we know about gold? What do we know about pure gold? Do we know what its density is? I think we do. 19.30 grams per milliliter. 19.30 grams per milliliter. Ooh. We have significantly fewer grams for every 1 milliliter in the ring than we should have if it were pure gold. So, I think that Alicia should probably, well, I don't think she should throw the ring at him because that's not necessary, but she might not treasure the ring as his first truly generous gift. I don't know, I think it's still nice that he gave her a ring. Maybe he didn't know it wasn't 24 karat gold. Maybe he got swindled or something. But in any case, it's not gold. It's not pure gold. There's our answer. All right, let's do number 8, and then I'm going to stop this video. This will be the last one for this video. A student filled a graduated cylinder with water and read the meniscus at 25.8 milliliters. The student then dropped a solid material into the graduated cylinder, and the water level rose to 35.9 milliliters. If the solid material had a density of 2.99 grams for every 1 milliliter, determine the mass of the solid object. So this is another water displacement question. All right, they filled a graduated cylinder with water and read the meniscus at 25.8 milliliters. Then we put a solid in there, and the water level rose to 35.9. So I'm going to draw my graduated cylinder. I'm going to show the initial volume of, what was it? 25.8. And then we put an object in there, and the water level rose to what? 35.9 is the final volume. If the solid material had a density of 2.99 grams, okay, let's figure out our volume first. Well, with the ring, we just subtracted these two volumes, right? So if we do 35.9 minus 25.8, we're going to get 10.1 milliliters is the volume of our object, right? And we also know it has a density of 2.99 grams for every 1 milliliter. Okay, let's write it like this. 2.99 grams is the mass of 1 milliliter. And then I need to figure out what? The mass of our solid object. We know the density in this case. We're trying to figure out the mass. We're trying to figure out the mass. So I'm going to match the G. I'm going to line it up under my other G. We know the volume of this object. We just calculated it. It's 10.1 milliliters, right? So instead of having 1 milliliter, we have 10.1. All right, is 10.1 milliliters bigger than or smaller than 1? Obviously, it's bigger than. How many times bigger is it? 10.1 times, right? So to get from 1 down to 10.1, we need to multiply by 10.1. We have 10.1 times as many milliliters on the bottom as we do on the top. If we have 10.1 times as many milliliters on the bottom, then we should also have 10.1 times as many grams on the bottom as we do on the top. So this becomes 2.99 grams times 10.1 times as many grams gives us what? Let's do the math here. 2.99 times 10.1 gives us 30.199. And around that to 30.20. Why not? 30.20 what? 30.20 grams. That is the mass of our solid object. All right, that's the end of this video. Let's see you in the next one.